Everything from your phone to the entire power grid, it all runs on electricity. But to really get a handle on it, you got to speak the language. So today we're going to break down the basic words, the fundamental variables that describe any electrical system. We're going to turn some pretty complex physics into a clear, simple map that anyone can use.
So, first things first, what even is an electric circuit? Well, when engineers talk about a circuit, they're not really talking about the physical wires and all the little bits and pieces. They're talking about a mathematical model. And it's a brilliant simplification, really. It lets us predict exactly how an electrical system is going to behave without getting totally lost in all the tiny physical details. You can think of it like this. A circuit diagram is like a map of a city. Now, the map isn't the city, right? But it gives you everything you need to get around. The roads, the landmarks, the rules of the road. Well, our circuit model does the exact same thing for electricity. It is an incredibly powerful tool for figuring stuff out. Okay, so here's our game plan. We're going to start by getting on the same page with a common language for measurement. Then we're going to meet the two stars of the show, voltage and current. After that, we'll see how they team up to actually do work, which we call power. And then finally, we'll learn a really crucial trick for checking our work to make sure our map is spot on.
Right, so before we can analyze anything, we all need to be speaking the same language when it comes to numbers. We've got to agree on the units. And that's where the International System of Units, or SI, comes in. It's what makes sure an engineer in Tokyo and one in Toronto are talking about the exact same thing.
So here's our core vocabulary. We're really just going to focus on these four. The ampere for current, the volt for voltage, the watt for power, and the joule for energy. Think of these as the building blocks for, well, everything else we're about to talk about.
All right, now it's time to meet the two most important players in any circuit. Seriously, if electricity were a movie, voltage and current, they'd be the big stars. And understanding how they work together is the key to, well, everything.
So let's kick things off with current. We use the letter I for it. All current is a measure of movement. It just tells us how much electric charge is flowing past a single point in a certain amount of time. And we measure this flow in amps, or you'll usually just hear amps. But, what makes that charge move in the first place? That's where voltage comes in. Voltage, or V, is the push. It's the pressure, the potential energy that gets the current moving. It's basically the work it takes to move a charge from one spot to another, and we measure that push in volts. And this is the easiest way to think about it. Current is the flow. Think of it like the amount of water moving through a hose. Voltage is the push. That's the water pressure that's making the water move. You see? In a real circuit, you can't have one without the other. One is all about the movement itself, and the other is about the potential for that movement to happen. Okay, so we've got our push and we've got our flow. But what happens when they actually start working together? Well, that's when we get to the cool stuff. Lighting up a room, charging your phone. This is where power and energy come into the story. Power, which we call P, is just the speed at which energy is being used or moved around. And the math is super simple. It's just voltage times current. You multiply the push by the flow, and what you get is the amount of work being done every single second. And we measure that in watts. Now, this brings up a really important question. When we're looking at our circuit map, how can we tell if something like a battery is supplying power versus something like a light bulb that's using it? We need a rule, a consistent way to tell them apart. And that rule has a kind of fancy name, the passive sign convention. Now, it sounds technical, I know, but the idea is actually super simple. It's the rule of the road for our map. All you do is look at which way the current is flowing. If the current goes into the positive side of a component, that component is absorbing power. It's using it. That's it. And here's where it gets really elegant. When we actually calculate the power, P equals V times I, the sign of our answer tells us the whole story. If the number is positive, power is being absorbed, like by a light bulb. If the number is negative, power is being supplied, like from a battery. It's a beautifully simple system. So we've got our terms, we've got our rules, but how do we know if we've analyzed a whole circuit the right way? Well, it turns out there's this amazing, built-in check that comes from one of the most basic laws of physics. And this is it right here. It all comes down to the conservation of energy. You can't just create energy out of thin air, and you can't make it disappear. You could only move it around. So in our perfect little circuit model, this means all the power being supplied has to exactly equal all the power being used. So when you add it all up, the grand total has to be 0. So here's how you do it. It's a dead simple 4-step process.
You just go through your circuit, one component at a time, and calculate the power for each one. You use that sign convention we talked about to make some positive and some negative. Then you add them all together, and if you did everything right, the final sum will be 0. I mean, it has to be, every single time.
Okay, but what if it's not 0? You do all the math and you get some other number. Does that mean you just broke physics? No, of course not. All it means is that there's a mistake somewhere on your math. Your calculations are off. For example, let's say you add everything up and you get negative 20 watts. That minus 20 isn't just a wrong answer. It's a bright red flag. It's your circuit model literally telling you, hey, go back and check your work. And this is why this is such a powerful technique. That power balance check is like a built-in diagnostic tool. It confirms your whole analysis is correct. If you get 0, you know you're good. If you get something else, it tells you a mistake was made. Maybe you flipped a sign somewhere, and it tells you that you need to go find it. So let's do a quick recap of our new circuit toolkit. Number 1, circuits are just useful maps, not the messy real world. Number 2, voltage is the push, current is the flow. They're the dynamic duo. 3, power, with its handy plus or minus sign, tells us who's supplying the energy and who's using it. And finally, number 4, in the end, it all has to balance out to 0. Which leaves us with a really interesting last question to think about. We've been talking about this ideal, perfect mathematical map, but the real world is messy. The components aren't perfect. So how do engineers actually bridge that gap between this clean world of theory and the messy reality of building actual stuff? Well, that's a great question for another time. Thanks for joining me.